Welcome to the deep dive, where we cut through the noise and deliver those crucial aha moments you need to stay genuinely well informed. Today, we're plunging into a topic that isn't just cutting edge, it promises to, well, fundamentally reshape how we perceive and secure our world. So imagine, if you will, a surveillance system. But not just any system. This one doesn't passively record everything all the time, in blurry, overexposed frames that just eat up storage and battery life. Instead, picture a camera that only really wakes up when something changes, ignoring the vast, static, unchanging background. It's almost like an eye that feels motion instantly rather than just seeing a series of pictures. Now, what if that incredibly efficient bio-inspired system could detect anomalies, those strange, unusual, maybe even dangerous movements with a speed and efficiency that, well, current cameras can only dream of, a system that gives you critical insight, not just, more data to sift through.
Yeah, this really pushes the boundaries of what we even understand as machine vision.
Yeah.
It's a fundamentally different approach, bio-inspired, like you said,
What?
and it challenges the very foundation of traditional sensing. It moves from being just a passive recorder to an active change-detecting observer. It's less about observing frames, I guess, and more about experiencing motion itself.
Absolutely. And that's why today our deep dive is into EVIM, neuromorphic event-based sparse anomaly detection, a really groundbreaking paper from Lakshmi Anomaly, Anirban Chakraborty, and Chetan Singh Thakur. This isn't merely about some new algorithm. It's about a paradigm shift, a completely different way of seeing and processing the world, directly inspired by, well, the intricate efficiency of biological vision.
Exactly. And our mission today is pretty clear. We're going to unpack exactly how these event-based cameras operate, explore why they represent such a monumental game changer for critical applications like, say, high-speed anomaly detection. And then we'll drill down into how the Evans system ingeniously leverages their unique properties to achieve truly remarkable performance with vastly reduced computational cost. That's the kicker.
Right. Get ready, because we're about to uncover how this research redefines what normal and anomalous truly mean to a machine. And crucially, how it tackles that huge challenge of information overload by being inherently sparse, only paying attention to what truly matters, discarding the noise right from the start. This isn't just smart, it feels elegantly efficient.
It really is. The elegance is in the efficiency.
Okay, so to really appreciate the revolution here, we first need to understand, the status quo. Most of us are pretty familiar with conventional cameras, right? The ones in our phones, our home security, dash cams. They're everywhere. They all work on a pretty straightforward principle. Capturing entire frames, basically taking a full snapshot of the whole scene at fixed intervals, like 30 frames per second. That's standard.
Indeed. And while that approach has been incredibly successful, I mean, it's the backbone of modern imaging, it really does come with a cascade of significant drawbacks, especially when you think about long-term use or autonomous systems or anything high speed. A core issue is just their inherent inefficiency. They consume a lot of power because they literally process every single pixel in every single frame. It doesn't matter if nothing's changed or if it's pitch black.
It's like having a full orchestra playing at full volume, even if only one violin needs to make a sound.
Oh,
It's
right.
rowash. Yeah. Which means if you're, say, monitoring a static hallway in an office building for hours, your camera is still burning through power, crunching data to record the exact same wall, floor, ceiling, over and over. Thousands upon thousands of frames of nothing new. It feels almost absurdly wasteful when you stop and think about it. Is that fundamental inefficiency the main driver for looking for new vision paradigm? Or are there other big problems event cameras solve?
That's a great way to put it, the orchestra analogy. The inefficiency is a huge driver, yeah, but it's definitely not the only one. Consider motion blur. Conventional cameras struggle with it badly, especially when things move fast, because they're trying to capture the whole scene in a tiny fixed window of time. Any rapid movement just smears across pixels during the exposure. You get a blurry mess. And then there's their limited dynamic range. They often struggle in scenes with extreme light variations.
Ugh.
Either you get those blown out highlights where all the detail is just gone, or deep muddy shadows where you can't see anything. Handling both at once. Very difficult.
Oh, definitely seen that. Those surveillance videos where half the screen is just a white blob or you can't make out a face in the shadows. It's maddening when you need that detail. But like you hinted, maybe the biggest issue, the one that really hamstrings these systems, is just the sheer volume of redundant data they generate. All those static backgrounds are recorded continuously, making huge files. They need storing, transmitting, processing, even though, yeah, 99% of the pixels might show nothing new.
This is exactly where event-based cameras step in. They offer a genuine paradigm shift. These are novel sensors, directly inspired by biology, specifically how our own retina works. Think about your peripheral vision for a second. Your brain isn't constantly processing every tiny detail in your whole field of view at full resolution, right? It's mostly registering changes. It's when something moves or flashes that your attention snaps to it. That's when your brain dedicates more processing.
So they're not taking snapshots, they're reacting.
Hmm.
Reacting to change, almost like a sensory organ instead of just a recorder.
That's an excellent analogy, yes. The key difference is their asynchronous operation. Instead of capturing frames at fixed intervals, they only record events. An event is generated only when an individual pixel detects a significant change in brightness. If a pixel sees a static scene, it just stays quiet, no data.
That sounds incredibly precise. So what is an event then exactly? Is it just a pixel blinking on or off?
It's actually far more sophisticated than that. An event, usually denoted as EEG, is a little data packet with four crucial bits of info. XKYK, TK, PK, XK, and YK are the exact pixel coordinates on the sensor where the change happened. TK is the incredibly precise time of that change, accurate down to microseconds. We're talking
Wow.
incredible temporal resolution, way beyond standard cameras. And PK is the polarity. It tells you if the brightness of that pixel increased, +1, or
Yeah.
decreased, meaning 1.
Wow. Okay, so it's not just that something changed, but precisely where, precisely when down to the microsecond and how brighter or darker. That is radically different from a normal frame where you'd have to compare two whole images to even guess that something moved.
Absolutely. And the fundamental design means if nothing changes in the scene, literally no data is generated. None. The camera is essentially silent, consuming minimal power. It automatically filters out all the static, irrelevant stuff right at the sensor level. Before any processing even starts, it's a huge head start.
Okay, let's unpack the practical advantages this brings. With that fundamental shift, what are the immediate tangible benefits for someone using these systems? Where does the efficiency really show up?
Well, the first one's pretty obvious. Extreme efficiency and really low power use.
Hmm.
Because only the active pixels, the ones actually seeing a change draw power, you get massive energy savings. Think about battery-powered devices, remote surveillance, sensors in autonomous cars that need to be always on. They aren't constantly burning power, just rereading static info. You could potentially deploy a system somewhere remote and have it run for months, maybe years, on one battery, only sending data when something actually happens.
That's incredible. So we're not just talking small battery gains, but maybe a fundamental shift in where we can even put cameras. Like a device sits dormant for months, then instantly activates using a fraction of the power. That sounds like it opens up monitoring for previously impossible locations, remote security, environmental sensing.
Precisely. And it doesn't stop there. Another huge advantage is their high dynamic range, HDR. Event cameras can capture detail across an incredibly wide range of light conditions. We're talking 120 to 140 decibels typically. That's vastly superior to conventional cameras, so you won't get those frustrating blown-out highlights or details lost in deep shadows nearly as much. They can effectively see everything, from the darkest corner to the brightest glare, at the same time, with clarity.
Okay, no more missing crucial details because of bad lighting. That's a huge deal for critical applications. And what about motion blur? That old problem with high-speed video or even just fast movements in surveillance footage?
Motion blur is virtually eliminated. Because they capture changes instantly at the microsecond level, they excel at recording high-speed movements without any blur at all. This opens doors for applications that were just impossible before, where fast motion would just be a smear. Think about robotics tracking fast parts or autonomous vehicles needing to react instantly to sudden changes in traffic, no matter how quick.
And this is where it gets really foundational and central to our deep dive today, the inherent power of sparsity. By their very design, they only encode relative motion between the scene and the sensor. They discard the static background completely. It's like they're hardwired to just ignore everything that isn't actively changing.
That's spot on. The result is a very sparse data structure. And this isn't just a side effect, it's a fundamental advantage that this Evan paper explicitly leverages for its computational efficiency. You're not getting a dense grid of pixels with mostly redundant info. You're getting this stream of discrete, highly meaningful events. Each one tells you something new and important.
So what does this all mean for real-world impact? What's the potential here?
Well, these low-latency sensors are already enabling incredibly agile robotic applications. Think high-performance drones navigating complex spaces at speed, or self-driving cars needing rapid, precise perception. However, despite the sensor's promise, the big challenge has always been developing robust and accurate visual analytics algorithms specifically for this unique, asynchronous, sparse event data. Most traditional AI models, they expect dense frames, so adapting them without losing the event camera's advantage is the speed, the sparsity that's been the major hurdle. And this is exactly where Evan makes its mark.
That brings us perfectly to the critical application this paper tackles: anomaly detection. We've talked about how event cameras are revolutionary, but why are they so uniquely suited for spotting the unusual? For flagging those subtle deviations that might signal a problem?
Well, the need for anomaly detection is just pervasive. It's growing across so many sectors. We're talking surveillance, obviously, intrusion detection, industrial monitoring, spotting equipment issues before they cause major failures, even healthcare, detecting unusual patient patterns or behaviors. It's really widespread.
But anomalous activities can be so subjective, can't they? What's normal in one place is a huge red flag somewhere else. Like someone running in a park is fine, someone running through a secure lab at 3 a.m. Definitely not fine.
That's a really important point. How do you define an anomaly for a machine effectively? Generally, the idea is that activities occurring with low probability in a given context are seen as anomalous. High probability activities are normal, but like you said, it's highly subjective. It depends entirely on the specific task and environment. For this specific research, the Evan paper, they set up very clear context-specific definitions for the dataset they built.
Right. And what were those? How did they draw the line for their system?
For this study, normal activities were primarily defined as a stationary background, just the camera observing an empty scene or a pedestrian walking naturally through the scene. The anomalies they focused on included things like running, bending over suddenly, falling, simulated fighting, and even vehicles appearing on a road where they shouldn't be. It's really crucial to remember these are context-specific for this research. They're designed to test the system's ability to pick up on different motion patterns.
Got it. Not a universal definition, but the targets for their tests. And in any of these cases, especially security or safety, a fast response is absolutely critical. You need to detect that anomaly quickly, ideally in real time, to do something about it.
Absolutely. The speed of response really depends on two things working together: the sensor's ability to capture the info quickly and the computational complexity of the algorithm processing that data. If the sensor is slow or the algorithm takes too long to run, you lose precious time. The detection might be too late to be useful.
So, considering all that, why are event cameras such a perfect fit for anomaly detection? What makes them stand out compared to traditional cameras?
It really comes down to their fundamental design and the data they output. First, they offer instant motion encoding right at the sensor level. Unlike traditional cameras where you need complex, often slow algorithms like optical flow to figure out motion from sequences of frames, event cameras naturally capture motion information as events. The very act of generating an event is a signal of change in motion. The sensor itself does a big part of the work that traditional systems need heavy computation for. It frees up resources downstream.
That's a huge head start. The motion info is just baked into the data stream. And for a stationary camera, which is common in surveillance, does that sparsity offer another leg up?
Yes, a profoundly crucial one. For a stationary camera, the event camera provides essentially automatic background subtraction. If the background isn't moving, it generates zero events from those pixels. This just eliminates a massive source of irrelevant data and computational load right at the source.
Ah.
No algorithm needed to figure out the background later.
Which means the data stream becomes even more sparse. It's like it's naturally filtering out the boring stuff.
Precisely. This pronounced data sparsity, especially when the camera is stationary, isn't just a nice bonus. It's a foundational element that Evan cleverly exploits. The computational burden drops dramatically because the network only has to process the actual events, not this huge grid of mostly static pixels. Imagine an AI that only even looks at the moving parts.
But if the data is so scarce and that's its strength, what's been the main problem for algorithms trying to use it? Why haven't event cameras taken over everything already if they're so good?
Historically, the challenge has been kind of twofold. First, converting this sparse asynchronous event data into a format that conventional, dense deep learning networks can understand. These networks, the ones driving modern AI, they expect full frames, dense grids of information. Trying to cram sparse event data into that dense format often meant losing the advantages. You'd basically re-densify the data, losing efficiency. Second, developing algorithms that could really leverage the incredible temporal precision of events beyond just where they happen spatially. Evan tackles both of these head-on.
Okay, so we have these super efficient sparse data event cameras. We get the need for fast anomaly detection. Now, how does Evan take this raw sparse info and actually spot an anomaly using generative AI? This feels like where the paper's real magic happens.
Yeah, the deep learning challenge with rare events is a big one. Traditional classification just doesn't work well. Anomalies are, by definition, rare. So training a standard normal versus anomaly classifier, it's basically impossible. You just don't have enough examples of all the weird things that could happen to train it properly.
Right, you can't feed it 10,000 examples of normal walking and 3 examples of person spontaneously combusting and expect it to work well. The imbalance is just too huge.
Exactly. So the really clever shift that Evan uses is generative deep learning, GDL. The elegant solution is to train a network only on normal activities. The network learns the intricate density model of what normal looks like. It becomes an expert in normalcy.
And then it uses that deep understanding of normal to predict. Like it develops an intuition for what should happen next.
Precisely. Anomaly detection then becomes a prediction task. If the network sees normal activity, it should be able to predict the next bit of normal activity accurately. But if an anomaly occurs, something that doesn't fit its learned normal model, the network fails to predict accurately. And this failure, this significant prediction error, that's the signal for an anomaly. It's basically detecting when its model of the world breaks down because something unexpected happened.
That's a fantastic way around the rare event problem. Super elegant. And Evan uses a specific type of generative AI, a conditional generative adversarial network, or CGN. For those maybe less deep in the AI weeds, can you give us the quick rundown on what a GAN is?
Sure, think of a Jan as a sort of two-player game. A bit like an art forger versus an art critic. You have a generator network that's the forger. It tries to create realistic data. In this case, it's trying to predict future event patterns. Then you have a discriminator network that's the critic. Its job is to tell if the data it's seeing is real from the actual camera or fake made by the generator. They constantly push each other to get better. The generator gets better at fooling the discriminator, and the discriminator gets better at spotting the fakes. It's an adversarial process that improves both.
Okay, so the conditional part of CGAN means it's not just making up random future data, it's guided by something.
Exactly. The conditional part is key here. The generator isn't just creating any future data. It's creating a future prediction that is conditioned on a current observed activity.
Hmm.
So it looks at the current motion patterns, encoded in that memory surface we'll talk about, and tries to predict the most likely normal next motion pattern, given that specific context. If it sees someone walking left, it predicts them continuing to walk left, not, suddenly teleporting.
Got it. And here's where Evan's breakthrough really comes in. The paper's core innovation is building this STN with sparse submanifold convolution layers. This directly tackles that problem we talked about. How do you process sparse event data without making it dense and slow? By using sparse convolution, Evan makes the CN inherently efficient for event data. It keeps that sparsity advantage all the way through the AI.
That's a really key insight. I mean, GANs and SKIANs have been used with event data before for things like turning events into images people can look at or building data sets, but using them with sparse convolution layers specifically for anomaly detection. That's the novel application here. Evan is applying this tech in a really targeted and effective way, embracing the sensor's native data format.
So it's not just what they use, but how they adapted it so carefully to the sparse nature of the data. That's the difference. And speaking of unique characteristics, anomaly detection relies heavily on understanding not just what's happening now, but how it's moving and what came right before. That temporal information, the motion history, is critical.
Absolutely critical. Traditional frame-based networks, the ones working on dense grids, they usually rely on computationally expensive techniques to get that temporal info. Things like optical flow explicitly calculating pixel movement between frames, or complex 3D convolution networks that treat video like a volume, or even recurrent networks like LSTMs built for sequences.
Hmm.
These work, but they add a lot of computational cost and latency.
But event cameras, they already have time baked in, right? That down to the microsecond. The paper mentions concepts like time surfaces, TS, and memory surfaces, MS, as ways they encode this. Can you help us visualize that? What's a good mental model? Is it like a surface where events leave a fading trace, like ripples showing time and intensity? How do they capture motion history?
That's a great analogy, the ripples. Imagine a digital canvas. Every time an event happens at a pixel, it's like a tiny, quick brushstroke, but one that starts fading immediately. A time surface, TS, basically aggregates these brushstrokes over a very short, fixed time window, say 50 milliseconds. It's a snapshot, but one showing the recent history of motion where things changed recently and how bright or darker. A memory surface, MS, takes that idea further. It builds more persistent, decaying memory of where and when things have moved over a slightly longer period. It's a fundamental way to summarize the history of change at each pixel, giving context beyond just the latest event.
Okay, that makes sense. And Evan introduces a big innovation here, the deep learning DL memory surface. So instead of manually designing how that history is summarized, the network learns the best way. That sounds powerful.
It really is. This is a novel, unsupervised deep learning solution designed specifically to learn a better sparse event memory surface. Instead of relying on, say, fixed mathematical formulas or handcrafted kernels to decide how memory fades, the network figures out the most effective way to represent motion history directly from the event data itself.
And the key benefit, it gets rid of the need for those computationally heavy optical flow calculations or 3D convolutions. That seems like a massive efficiency game right there.
A huge gain, yes. It bypasses those complex steps entirely.
Mhm.
And this brings us to another critical aspect. This learning is unsupervised and data-dependent, but not task-dependent.
Okay, what does that mean for us, for practical use? Unsupervised and task independent.
While unsupervised means the learning process for this memory surface doesn't need labeled examples like this is normal running or this is anomalous falling. It just learns how to efficiently encode any motion history from the raw event stream. Task independent means the way it learns to represent motion isn't tied specifically to the anomaly detection task. It's learning a general purpose motion representation.
Ah, so it's decoupled. The part that learns how to represent motion is separate from the part that uses that representation to detect anomalies.
Precisely. And this is incredibly versatile. It means the same learned memory surface could potentially be applied to any video analytics task involving motion tracking, action recognition, whatever, even if you don't have much labeled event data for that specific high-level task. This modularity is a massive win for flexibility and efficiency, especially since getting large labeled event data sets is still quite hard.
Let's double-click on this deep learning memory surface then. It sounds like a real powerhouse for Evan. What exactly is it architecturally? How does it stay compact but informative?
Okay, so the DL memory surface is essentially a single 2D structure. Think of it as a highly compressed, intelligent summary map. Its purpose is to embed that rich motion history from the event stream in each pixel, but in a remarkably compact, learnable format that the next stage, the CGN, can use immediately.
So it's like a smart summary of what's been moving where for how long at every point, not just a raw data dump. And crucially, it learns this summary.
Exactly. And what's insightful is that it moves beyond older methods that used handcrafted features. Traditional techniques might use fixed mathematical kernels like exponential decay filters to summarize motion. But choosing the right kernel often required a lot of domain expertise in fiddling with parameters. Evan's approach learns this representation directly from the data. The network automatically figures out the best way to capture motion history for whatever dataset it's trained on.
And that unsupervised task-independent advantage you mentioned, how does that really break the mold compared to previous methods? Why is it so important it's not tied to a specific goal?
Well, many previous end-to-end learning methods for representing event data were task-dependent. They were optimized specifically for, say, object recognition. If you then wanted to use that representation for anomaly detection, it might not be optimal. You might have to retrain or even redesign the whole representation learning part. That's inefficient.
But Evan's versatility comes from this independence. So for you, the listener, this means the same learned memory surface could be reused across different motion analysis tasks. That's a huge win for flexibility, especially when labeled data is scarce.
Absolutely. It makes the whole system way more adaptable. It neatly separates the problem of how do we represent motion efficiently from the problem of what do we do with that motion representation.
Yeah. Let's get a bit technical on the structure. What does the architecture of this DL memory surface generation network look like? How does it stay so computationally cheap?
It's designed deliberately to be shallow and efficient. It's basically a preprocessor, so it needs to be fast. It uses a fully convolutional encoder-decoder structure. The input is what they call a discretized volume of event data, or EV. This EV is formed by taking the raw events and stacking them into time surfaces, those snapshots of recent activity, over short time bins, maybe 15 milliseconds each. So you get this small 3D chunk of recent event data, XY, time.
Okay, so it takes a little burst of events, organizes them into a mini 3D block, and this goes into an encoder.
Exactly. This input volume goes through the encoder. At the narrowest point, the bottleneck layer, it extracts a single-channel DL memory surface, EMS. This EMS is the compact, learned summary of motion history. The decoder part then tries to reconstruct the original input event volume, EV, using only this single M surface. The network learns what information is absolutely essential to keep in M's in order to be able to reconstruct the input. This forces the bottleneck to capture the most important motion features.
And what's the clever trick for learning the temporal features without getting computationally heavy?
The really neat part is the use of 1D convolution layers, applied only across the time dimension of that input event volume. This constraint forces the network to learn temporal kernels, essentially, optimal ways to accumulate event data over time, like learning the best decay functions without messing up the spatial distribution of events. It results in a relatively small but powerful network that gets really good at understanding the timing and sequence of events efficiently.
That's a really smart design. Focus the learning on time without blowing up the computation. How does it actually learn, though? What's the intelligent loss function guiding this unsupervised process?
The loss function has two main parts working together. First, there's the data term. The goal here is simply to make sure the reconstructed event volume at the output is as close as possible to the original input volume. This usually boils down to minimizing the mean square error, MSE, between the original EV and the reconstructed EV, basically. Learn to compress, but make sure you can rebuild the original accurately.
Okay, makes sense. Compress but preserve information. And the second term is for sparsity, which is so vital for event cameras.
Yes, the equally critical sparsity term. Its goal is to maintain the inherent sparsity of the event data within the bottleneck layer itself within the DL memory surface. This is crucial. We don't want to lose the efficiency gains by making this intermediate summary dense and computationally heavy. They achieve this using a combination of L1 and L2 regularization on the activations in that bottleneck layer. This gives them knobs to control how sparse that learned memory surface is.
Okay, L1 and L2 regularization. For those less familiar, can you quickly explain why those tools are good for enforcing sparsity? What do they tell the network to do?
Sure. Think of L1 regularization as being quite aggressive. It strongly encourages the network to set many of its internal values, weights, or activations to exactly 0. It effectively prunes connections, making the representation sparse. It's great for feature selection, only use what's absolutely necessary. L2 regularization is gentler. It encourages values to be small, but rarely pushes them exactly to 0. It helps prevent extreme values and stabilizes the model, preventing overfitting. By using both, they get fine-grained control. L1 drives the actual sparsity, making M's lean, while L2 keeps things stable. It ensures the motion summary stays as efficient as the raw event data it came from.
All right, so we've got the event cameras, we've got the clever DL memory surface summarizing motion history efficiently. Now let's put it all together, the full Evan anomaly detection method. How does this sparse CGAN actually work in practice? From those raw microsecond events to a clear something's wrong signal.
It's a pretty clear pipeline, designed for efficiency all the way. First, there's a bit of pre-processing. Raw event data can have some sensor noise, so they clean that up first to get a reliable stream. Then, this clean event stream goes into that unsupervised DL memory surface network we just discussed. That generates the crucial sparse memory surface, EMS, encoding the recent motion history.
Okay, so that sparse EMS summarizing the past motion becomes the main input to the CGAN.
Exactly. The sparse convolutional CGN is then trained using two key things. That DL memory surface EMS, representing the past context, and the actual future time surfaces, representing what really happened next. And critically, remember, it's trained only on normal activities. Its goal is to learn to accurately predict the normal future time surface, given the current motion history in MIGEN. It becomes a master predictor of normal continuation.
And crucially, how does it handle this EMS input and its own internal workings to maintain that sparsity? That's where other attempts often fall down, right?
This is absolutely foundational to Evan's success. The DL memory surface EMS is fed to the CGN's generator not as a dense image, but as a sparse tensor. This data format is key. It saves memory and maintains computational sparsity throughout the entire network. They avoid that trap of converting sparse data into a dense format just to feed it into standard AI layers. Every layer in their CGN is designed to work natively with these sparse tensors.
Let's talk about the heart of this CGN, the generator. It uses something called submanifold sparse convolution, SSC. What's the core idea behind SSC? Why is it such a good fit?
The core idea of SSC is really elegant and perfect for this data. Instead of performing convolutions across all pixels in the input, like dense networks do checking every window in a building, SSC computes convolutions only on active sites. An active site basically means a pixel location where there's actually some non-zero data, like an event represented in the sparse tensor.
So if I picture it, a normal convolution checks every window in a huge building, even if 99% are dark. but SSC only even looks at a window if the light's on or someone's moving inside. Is that a fair way to think about how it cuts down computation?
That's a perfect analogy.
Oh.
Exactly. It intelligently skips over all the empty static regions, drastically reducing the number of calculations. The generator itself uses an encoder-decoder architecture. The encoder has, I think, 6 convolution layers and 5 pooling layers, getting progressively deeper from 16 channels up to 512, compressing that sparse data into rich feature maps. The decoder then reverses this with 6 deconvolution and 5 unpooling layers, reconstructing the predicted future time surface from those compressed features.
And it uses specialized Minkowski layers for this, designed specifically for sparse data.
That's correct. These are specific building blocks, convolution, pooling, activation, all optimized to work efficiently on sparse tensors, using libraries like the Minkowski engine. This is where the massive computational savings really happen, especially during inference when the system is actually running live, detecting anomalies. Building the generator with SSC and these layers leads to that incredible efficiency.
Okay, so the generator predicts the normal future. What about the discriminator, the critic? It uses something called patch-GAN. How's that different?
Right, the discriminator uses patch-GAN. It's a clever twist on standard discriminators that just give a single real or fake score for the whole input. Patch-GAN is actually a convolutional network itself, but instead of outputting one score, it looks at overlapping patches or tiles of the input image.
How does classifying by patches help with spotting anomalies, especially subtle ones in event data?
Instead of one global verdict, PatchGAN classifies each tile of the predicted future time surface, and the real one, conditioned on the memory surface, as real or fake. The overall decision is based on the average across all patches. This approach is great for event data because it forces the discriminator to look at local details, like sharp edges and textures, which is often where crucial motion information lies in event streams. A global discriminator might get fooled if most of the scene looks normal, but PacGAN scrutinizes local consistency across the whole prediction. It also works well on inputs of any size.
This sounds incredibly innovative on paper, a really elegant solution, but, the proof is in the pudding. Let's talk validation. How did they actually prove Evan works and that it's better?
Well, a critical first step and a major contribution itself was building a brand new dataset. It's pretty remarkable. Before this paper, there was actually no existing public dataset specifically for event-based anomaly detection. They had to create one from scratch.
Wow, so they didn't just build the algorithm, they built the benchmark for everyone else, too. That's huge for the field. What did this ANA dataset contain?
It was a careful mix. They recorded new data themselves in different settings, an indoor lab, an outdoor corridor, using a Davis event camera, which captures both events and standard frames. That was 346 by 260 resolution. Then, to make it richer, they brought in relevant samples from existing event datasets focused on pedestrian detection and action recognition. And crucially, they staged clear normal activities, walking, static background, and a diverse set of anomalies, running, fighting, bending, falling, even vehicles showing up where they shouldn't.
And what made this dataset particularly challenging? Because making a dataset where anomalies are super obvious doesn't really prove much, right?
Exactly. This is a key point they make. There's significant overlap in the event rates between normal and anomalous activities. So someone walking quickly might generate a similar number of events per second as someone starting to run or bend over. Figures 3 and 4 in the paper show this visually with histograms. You can see the overlap. This means you can't just use a simple threshold like alert if event rate goes above X. A fast walk might trigger it just as easily as a real anomaly. It really underscores why you need a deep network that understands the patterns and sequences, not just the raw activity level.
That's a really key detail. The rate isn't enough. It's not just how many events, but the signature of those events. Can you elaborate on why that makes simple stats useless here? And how does Evan's approach with the learned memory and Xian become better at telling apart a normal fast walk from a truly weird movement, even if the event counts are similar?
That's precisely it. Simple statistical models or basic thresholds on event counts would just drown you in false alarms. Imagine a security alert every time someone hurried down the hall. Useless. Event rates alone just can't distinguish the nuances. A brisk walk and someone starting to run might look similar just based on event density for a short moment. Evan's DL memory surface helps here because it learns a rich temporal representation. It's not just counting events, it's encoding their history, sequence, and spatial spread over time. This lets the CGN learn the complex dynamics of normal motion. It learns the typical flow, the spatial patterns, the timing of a normal walk. So when it sees a similar rate of events but with a different spatial pattern, or weird acceleration or unexpected interactions like falling, its prediction of what should come next fails badly. That signals the anomaly. It's learning the grammar of normal motion, not just the volume.
Okay, so it's a tough data set that really demands intelligence. How did they measure performance quantitatively?
They used a standard set of classification metrics adapted for this task, things like recall, precision, F1 score, and accuracy. Just to quickly recap for everyone, a true positive here is correctly spotting an anomaly. A false positive is wrongly flagging normal activity. You want few of those. And a false negative is missing a real anomaly, potentially the worst error.
Right. And they also used equal error rate, EER. What's that signify?
EER is a really useful single number summary. It's the point on the ROC curve where the rate of false alarms, false positive rate, equals the rate of misdetections, false negative rate, which is 1 minus true positive rate. Basically, it finds a balance point between those two types of errors. A lower EER is better. They also showed the full ROC and precision recall curves for a complete picture across different detection thresholds.
So the main event, Evan's performance. What were the key results showing it worked well?
Well, first, the visual proof of anomaly localization is really compelling. Figure 5 in the paper shows it clearly. You see the event time surfaces from the recent past, T1, and the present T. Then, crucially, a third image shows the difference between the actual future TS and the one Evan predicted. These differences are highlighted in red, and the observation is striking. For normal walking, there's almost no red difference. Evan predicted it accurately. But for anomalies like kicking or picking something up, you see these prominent red blobs right where the anomaly happened. It shows the network failed to predict it and thus localized the anomaly. You can literally see it spotting the weirdness.
That's super intuitive. You can just look at it and see, I'd expected this, but that happened instead. Very clear. And quantitatively, did the prediction error match this?
Absolutely. Figure 6 shows plots of the mean square error, MSE, between the predicted and actual future over time. The pattern is exactly what you'd hope for. MSE stays consistently low during normal activity, but it spikes significantly during anomalous events. This confirms that core GNL principle. The network struggles to predict things outside its learned normal model, and that struggle itself is the anomaly signal.
That's the hypothesis proven right there. But how did Evan do against the established competition, the state-of-the-art frame-based methods?
This is where it really delivers a punch. They compared Evan against several top frame-based deep learning anomaly detection networks, labeled ANODET-AF. The key finding, shown in Table 6 and Figure 9, is that Evan achieved an AUC area under the curve of 96% and an ER equal error rate of 13%. This consistently outperformed all the conventional methods, which had AUCs ranging from about 59% up to 93% and ERs from 11% up to 43%. It's a clear, significant win for Evan in accuracy and robustness.
So it's not just good, it's demonstrably better than the previous best, even on those tricky anomalies.
Exactly. Even for those subtle anomalies like kicking, picking, or sit, the ones with event rates similar to normal walking, Evan still showed strong performance. Details in Tables 3 and 4, Figure 7. This really highlights its ability to understand the complex patterns of motion, not just the amount of motion.
Okay, now for many listeners in robotics, embedded systems, edge AI, here's the real jaw dropper. Computational efficiency. The paper shows a massive reduction. What metric did they use for that?
They used FLOP's floating point operations. It's a standard, hardware-independent way to measure how much computation an algorithm needs. Allows for fair comparisons. They contrast the theoretical FLOPs for dense versus sparse convolutions to show why sparsity helps so much.
And the numbers, they're almost unbelievable, right? It's not just a bit faster.
They're genuinely staggering. Conventional frame-based methods they compared against, like Gravenbach et al. Or Liu et al., need something on the order of 2.8 by 1010 to 6.4 by 1010 FLOPs per inference. That's tens of billions. Evan, because it leverages sparsity so effectively, they give an example where only about 6% of sites are active, operates at an astonishing 8.6 by 1 in 6 FLOPs. That's single-digit millions.
Wait, hold on. Tens of billions of operations down to single-digit millions. That's a reduction of thousands to tens of thousands of times. It's like replacing a supercomputer cluster with a decent laptop and getting better results. It almost sounds too good to be true. Was there like a single aha moment that led to this, or was it gradual optimization?
It feels like it was the culmination of really understanding both the event camera physics and how sparse networks work. The
Hmm.
aha wasn't maybe one single trick, but the realization that if every component, the memory surface, the generator, the discriminator, was designed from the ground up to embrace sparsity instead of fighting it or trying to fit it into dense frameworks, then this massive efficiency could be unlocked. Each piece was built sparse native. And this huge drop in computation isn't just academic bragging rights. It means real-time, highly accurate anomaly detection becomes genuinely feasible on resource-constrained hardware platforms.
So we're talking tiny drones, embedded systems in cars, low power security cameras, maybe even wearables, things that simply couldn't run those billion FLOP models before. This changes where advanced AI can actually be deployed. That's huge. This has been a truly fascinating deep dive into Evan, neuromorphic, event-based, sparse anomaly detection. It really feels like we're seeing a pivotal moment in machine vision unfold. Let's just quickly recap the core innovations we've covered.
Yeah, absolutely. We've seen how event-based cameras just fundamentally change how visual information is captured. They give incredible advantages in speed, dynamic range, power efficiency, all through that inherent beta sparsity. They're less about static images, more about experiencing change, much like biology does it. It's a total rethink of the sensor itself.
And Evan brilliantly builds on this foundation. It introduces what's really the first event-based, sparse, convolutional model specifically for anomaly detection. It's not just adapting old tech, it's leveraging the unique strengths of these new sensors right from the start. Recognizing the input data itself is key.
A huge piece of that is the novel, unsupervised deep learning memory surface. This smart component efficiently encodes that complex motion history from the event stream, completely bypassing the need for heavy traditional methods like optical flow. It learns to create this compact, rich summary of motion without needing any explicit labels.
And finally, the system masterfully uses that sparse convolutional CAN, which is just brilliant because it leverages every bit of the event data's natural sparsity. This lets it detect anomalies with really high accuracy while slashing the computational complexity by orders of magnitude, thousands, even tens of thousands of times less compute. That's a monumental leap in AI efficiency.
And the real-world impact here is profound. This isn't just theory. It's a practical, potentially deployable solution for real-time applications where every millisecond and every milliwatt counts. It brings advanced AI to places it couldn't go before.
Imagine smarter, faster surveillance that doesn't get bogged down in useless data but reacts instantly to genuinely weird activity. Think about more agile robots that can respond to unexpected changes with microsecond precision, or even safer autonomous vehicles spotting hazards with incredible efficiency, making those critical split-second decisions.
This research really drives home the point that how we sense the world and how we represent that data can be just as crucial, maybe even more crucial, than the AI algorithms we throw at it, which raises a really interesting question for you, our listener, to think about.
What other dense computational problems out there? Problems currently eating up massive resources. Maybe in other types of sensing, data analysis, even scientific modeling might be radically transformed if we just reconsidered the fundamental nature of the input data itself. Just like the event camera rethinks vision. What if rethinking the input isn't just an optimization, but maybe the ultimate shortcut to unlocking completely new levels of efficiency and capability across AI? That's all for this deep dive. Join us next time as we continue to unpack the cutting edge of science and technology, giving you the insights you need fast.